So I did C, and I'm going to see if that helps. And then if I want you to try D and see how far you get, or see if you finish it, and then let me know what further questions you have after seeing C done. So, okay. I rewrote it. It just rendered terribly onto Google Docs. So if n is less than 2, t of n equals c. If n is greater than 2, t of n equals 2 times t of n over 2 plus n cubed. So first thing I did, similar to what you did, t of n equals 2, t of n over 2 plus n cubed. And you say, well, what does t of n over 2 equal? Well, it equals 2 of t n over 2 times 2, which you wrote n over 4. These are, the same thing, plus n over 2 cubed. And then you say, okay, well, what does t of n over 2 over 2, or over 2 times 2 mean? And as you know, it is 2 of t of n over 2 over 2 over 2 over 2 cubed plus n of 2 squared plus, or to the power of 3. And it's recursive. It's a recurrence relationship, and it'll just keep going back until it hits the base, which is 2. And less than 2. So many 2's in this problem. Okay, so then plugging it in to see what it looks like. I made the parentheses different colors just to keep track of it. For some reason, it's harder to keep track of typed parentheses. It looks like scheme. So when I plug it in, going k equals 3 back, notice that n still equals the same thing. This is t of n, but all that we're counting here are more k's, which are like, you can think of as like recursions back, 3 iterations back. Think of them as iterations or recursions, whatever. It's the same concept. 3 deeper into the rabbit hole of, okay, well then what does t over n times 2 to the third mean, So k equals 3. And this is what we have. Our innermost plugin, which is right here, wrapped in the second innermost, which is right here, and then our outer, which was our initial 2 times t of n over 2 plus n cubed. And this is what we have when we go k equals 3 iterations in. With it written this way, it's easy to see the pattern. It's easy to see, but it's not easy to really mess with it at all. So what I did was distribute out these 2's first. So going from the center out, distributing out the 2's, we can get rid of some of these like nested formulas and just wind up with like our, an equation without a bunch of parentheses. So our first term, and we know k equals 3 iterations in, and 3 2's, 2 to the third times n over 2 to the third. And the rest of these terms, we notice that we went k in, and there are k of them. There are 3 of them. We add 1 on with each iteration inwards, but it's not the same exact thing that we're adding on. This was our first one that we started with, and then when we went another iteration in, we had 2 times n over 2 cubed. And then when we went another one in, 2 times n over 2 times 2 cubed. So, if we were going to go another one in, you could see there would be 3 2's here, and then 3 2's here. So we see what's going on. This we don't need to represent with a summation, but this is going to be pretty difficult to represent without a summation, as we're adding on a new term with each cycle. So if we simplify that down, we wind up with something like this. K is our iterations down. T of n over 2k, that is how our inner n is going to change each time. And now over here, I saw that, let me just check. Okay, so I saw that you had it written such that the only like variable in here was n, but that is going to trip you up because you notice that k doesn't have to equal n. At some point in the equation, if we like track everything, for any n 2 to infinity, k might equal n, but generally that doesn't have to be the case. Like if you look at this first one, k equals 1, n could equal anything. K equals 2, like k is going to change, so we need two different letters to represent each of these because they're not equivalent. So k is what was chosen. We're just going to use k. And then in the summation, we need another different letter to represent that variable because it's not k. In the summation, we see, okay, k equals 3 or k equals whatever it would need to equal for there to be 3 2's here, but there are only 2 2's here. So ultimately in the summation, it's going to start at choose I as the variable for that. I is going to equal 0, and it's going to go until k minus 1, which is what's happening here. K minus 1. So in this one, it would have been 2 to the 0, which is 1. And then m would have been over 2 to the 0, which is 1, so it's just n. Anyway, this is the summation we wind up with. And we use different variables to represent the numbers in the summation. The only one that we keep the same is n, because n is like from our original equation. It's right here, and it's just a part of what we're summing. So we're going to look at this first term in here, and we know that once it hits 2, it's going to be constant, and we also know that n is supposed to go from 2 to infinity, and eventually the denominator of this, n over 2 to the k, k is going to get big enough such that whatever n is, 2 is the 2 below is going to be growing more quickly, and the denominator is going to decrease. Or I'm sorry, I didn't say that right. The denominator is going to increase, so the fraction overall is going to decrease. Like limits, in the what is it as k approaches infinity? Because we just saw that k can change and n can stay the same. So as k approaches infinity, this inner fraction is going to approach 0, which is less than 2. So eventually, this is going to hit a constant status, which means that our growth is over, and we can just replace it with a c. So that simplifies things. Now, we're going to look at this side of our equation, this summation that we just put together. We don't want it. We want to find a way to get rid of it. First thing that we can do is pull n from our summation. Like it's right here, but it's not like to the power of I or anything like that. Like we can do without, it's not necessarily changing with each I. N is staying the same, but it's just being manipulated by this term, and this term. So we want to break up this fraction in here and eventually extract the n, because however 2 to the I and, this lower denominator to I to the third, like no matter how they grow, at the end of the day, it's going to be the same as if n was like out here and just multiplying by them. So, okay, so we want to extract n. We're going to break up this fraction right here. And we do that by, it's with exponents, this is n to the third over 2 to the 3i, really. So once we know that, we can just pull it out. So it's 2 to the I times n to the third times 1 over 2 to the 3i. And from here, it's obvious, okay, well, we can just pull this out now. The two that need to stay in are the two that are like connected to I, like they're dependent on, this summation. So pull n to the third out, and now we have these two left in our summation. We can simplify them further because, 2 to the I over 2 to the 3i, we're just going to wind up with, 1 over 2 to the 2i, that these cancel out. And then now that we have 2 to the 2i, we can just, if we know what 2 squared is, we can replace it with 4. So 1 over 4 to the I is where we go. Professor Brightsman mentioned a geometric series, so we're going to use that. This is a formula for a geometric series, and it pretty much says that if you can make your summation take the form of this, you can just swap the whole thing out for this. They're equivalent, so we can do that. Fortunately, our summation is already here. Our summation is going to go from 1. Our summation goes from 1 to k minus 1. So we don't have to worry about this up here because that's already what we have going. So plugging in the values, you're like, these don't necessarily look the same, but if we can plug in 1 for a, because technically this is, times 1, then r is 1/4, and and then we wind up with 1 over 1 minus 1/4, which equals 1 over 3/4, which equals 4/3. And we can replace our entire summation with 4/3, which really simplifies things. So we went from this like crazy problem to this. And as we know, if we're looking at big O, the constant doesn't matter. 4/3 doesn't matter. What matters is n cubed. So our big O is now O of n cubed. And we're done. That's it. That's it for solving the recurrence. We have a good closed form, and we're in a good spot.